Thank you very much for coming early in the morning to listen to this talk. After, forget now, 2-3 days of partying, it's nice to come back to familiar surroundings and listen to some mathematics. What I'll try to do in this hour is to present the history of large deviations. Of course, I can't describe everything that happened on the subject, but hopefully I'll be able to highlight some of the main steps involved in its development. Of course, I can't be up to date either. The history will stop at a certain point because it's a subject that's still very much happening, and as we speak, perhaps new results are being obtained. So let's begin at the beginning. The subject was born in Scandinavia, not very far from Oslo, in Stockholm, in fact, in 1932. And the person involved is Escher, who worked for the insurance industry. So you can see that the subject is very much applied, and his results were published in the Scandinavian Actuarial Journal of that time. He was interested in a very practical problem. As an insurance industry, you set aside a certain amount as reserves to be paid against claims, and he was worried that the total claim might exceed the amount of money reserved to pay for it, and then the directors of the company would be in some trouble. So the number of claims, he assumes some kind of a Poisson distribution, and the amount of claim, which could vary from claim to claim, is assumed to be independent, identically distributed random variables. So the problem, in some sense, amounts to estimating the tail probability of sum of a certain number of independent random variables. The number of claims itself is random, n is itself random, but we can handle that separately. So if we can analyze this behavior for large n, then one can analyze what happens. Or one could also think of it as n representing the number of clients, and then each xi would have 0 with some very high probability because the person may not find a claim. And then if he finds a claim, then you can have a distribution for it. So in some sense, the mathematical problem involves estimation of the probability that the sum of a large number of random variables exceeds another large value. The number A itself will be very large because larger than the mean in any case. So if we denote by mu the expected value of xi, then the expected value of the sum is n times mu, and if A is larger than mu, what is interested is in the tail. And you can use a central limit theorem as an approximation for this, and then if you do the actual central limit theorem approximation, then the probability one expects to be roughly the tail of a Gaussian, the point square root of n. That value is the normalized value of NA when you make the normalization needed for the central limit theorem. So mu here is the expected value, and sigma square is the variance. But this approximation is not good if A minus mu is not small. Now you can ask, how can it be not good? Central limit theorem is always valid and the approximation should be good. But the central limit theorem only tells you that the difference between these two terms goes to 0. But if A is larger than mu, both terms individually are small. So you have two small terms and the difference always goes to 0, but one could be much smaller than the other. So in that sense, the reason why this is not a good approximation for this is not because the difference is big, but because the ratio is big. So you would like to estimate, if the probability is as small as 10 to the minus 10, and if you estimate it to be 10 to the minus 3, that's not a good estimate. Okay. So Escher's idea involves what's called tilting the measure. And this is called, some people call it Khmer Transform, but I think the idea goes back to Escher. And Khmer, soon after, I think worked with Escher and generalized it to a wider class. Okay. Now this Escher still involves adding an exponential weight to the probability distribution and normalizing it so that mh is just the expected value of e to the hx, so that this whole thing is again a probability distribution. So you add more weight to larger values, and so it's a slight tilting of the probability distribution. And then you can estimate the probability involved, which is just, without using the central limit theorem, the probability in question is just a multiple integral evaluated over a certain region. That's the tail probability. And you can estimate it. Before you estimate it, I throw in some factors. I haven't really done anything because whatever I have done here, I have undone here, and whatever I have done here, I have undone here. So I haven't done really anything. Okay. Now, the transformed measure, dg, is that measure. So you can absorb this with the measure and one of the mh and change f to a g. If I do that, then it reduces to this integral. And so whatever is missing here went into the definition of g. Now I have the problem of how to pick my tilt. How much should I tilt by? So the constant h is to be picked. And you pick h so that the expected value of the random variable under the distribution g, that is, rather than the original average, you do this weighted average with the weight e to the hx, then the mean, instead of being mu, is a. Since you are going to shift the mean to the right, you need a positive h. The weight should be more to the right. And then if you call rho of a the product e to the minus h of a times m of h, and the corresponding variance is sigma square h, then you can rewrite the probability in this form. The advantage in having the probability in this form is that G is a distribution for which A is the mean. So now you are no longer interested in tail probability, you are interested essentially probability to the right of the mean. So if it weren't for this factor, central limit theorem would say this probability goes to half. But this factor does make a difference, but it doesn't make that much difference. You can renormalize, and if you write standard Gaussian approximation, you get such an approximation for Pn of A. Now this approximation is pretty good because you have e to the minus x squared by 2. The only bad term is this, and this integral you can calculate explicitly, and it's explicit form. So Escher's method gives you an asymptotic formula for this, which involves rho of A, And if the original distribution is not Gaussian, rho of A is not e to the minus A square by 2. And whereas if you did the central limit theorem approximation right away, it would give you rho of A is equal to e to the minus A square by 2, which is not correct. So this is the idea behind Escher's transform. And then you can redefine things just for the answer to be expressed in a much simpler form. So you are using only positive values of h, but you can still define all values of h and define this function I of x to be the Legendre transform of the log of the moment generating function m of h. Then I of x will be a non-negative function. It will have its minimum at the mean. It will be positive on either side, and you can recognize log of minus log rho A as just the infimum of I of x or x greater or equal to A. And if A is larger than the mean, this is exactly I of A. So then, if you redo the calculations and reinterpret what one gets from Escher's method, is that the log of the probability that the mean lies in an interval decays exponentially in this manner. And if the interval contains the mean, then the probability should go to 1, and then this infimum would be 0, because I vanishes exactly when x is the mean. So this gives you exponential decay if the interval does not contain the mean, and no decay if the interval contains the mean. So now this was extended in a much broader context by Khmer. Actually, in the way I have stated it, some of it is also Khmer's form of stating it, but this goes back to Khmer year 1938. Then years later, in testing of hypotheses in statistics, one is interested in estimating the power of certain tests and so on. In that context, Hermann Chernoff calculates this exactly by a similar transform and publishes this paper. And from that point on, the Escher estimates, which are called Khmer estimates, are now called by statisticians as Chernoff estimates. And then in 1957, Sanow gets into the picture, and he looks at the multinomial versions of these things. So here you have an experiment which can result in a certain number of possibilities, and these possibilities have probabilities P1, P2, a finite number of probabilities. So you can think of it as putting things in pigeonholes or cells, and PIs are the probabilities for the cells. So when you actually perform the experiment, you can have frequencies quite different from the theoretical frequencies, and you calculate the ratios, and these are the empirical probabilities, and we call them QIs. So the QIs are random, or PIs are the population values, and if n is very large, the law of large numbers says that with a very high probability, the QI is very close to PI. So one is interested in the large deviation properties of Q. So one has this function, the relative entropy or Kullback-Leibler information of Q's with respect to P is the summation Qi log Qi over Pi. By Jensen's inequality, this is always non-negative, and one can check just by doing the maximization needed to calculus to check that this function is also the Legendre transform of this object. So one can recognize this as a, does the indicator show there or not? Yeah, it does, okay. So one can recognize this as a multidimensional version of Khmer's theorem. And the way you see that is, you count the number of observations in a given cell is just counting. So Fi of xj is 1 if xj is equal to I. It's equal to 0 if xj is not equal to I. This was just counting various types of observations that you have. So you can think of a random variable which can take the values along the coordinate axis E1, E2, Ek, as many cells as there are, and each value is taken with probability P1, P2, Pk. Then you have a distribution in some higher dimensional space, and the moment generating function is just this, because theta dotted with Ei is just theta I. So this is the moment generating function of the random variable Q. And the law of large numbers is just for the average of Q, because the average of various values of Q is just the empirical probabilities. So one can interpret the large deviation of Sarnoff as just the multidimensional version of Khmer's theorem, which is originally proved for the real line. Now you can prove it for the vector value things. So then you can generalize this one step further. For instance, instead of looking at multinomial distribution, which is essentially a discrete distribution which can take a finite number of values with certain probabilities, you can generalize it to independent, identically distributed random variables from an arbitrary space X. So you have random variables from some space X with a common distribution mu. And then the empirical distribution is just you place mass 1 over n at these n random points that you have as observations. So you have a random measure nu sub n, which is the empirical distribution. So the empirical distribution Qn is just a random variable with values in the space of probability measures on X. So the distribution of nu n is just a measure Qn then on the space M. So one should think of Qn as the distribution of the empirical distribution. It takes a while to say it, but you can visualize it. So you have the random measure, and this is the distribution of the random measure. So it's a measure in the space of measures. And the law of large numbers says that if n is very large, this measure is concentrated very close to mu. So that just means that with a very high probability, your empirical distribution is very close to the theoretical distribution. That's the, if that weren't true, we couldn't do any statistics. So now the question is there a large deviation here? And if so, what is the rate function? And it's basically Sarnoff's theorem, because Sarnoff's theorem, if you go back, the rate function here you see is this. You can reinterpret this as sort of a relative entropy of Q with respect to P. The role of Q later on is played by lambda, and the role of P is played by mu, and the Radon derivative is d lambda over d mu, and you take the log of that and you take the expectation with respect to lambda, and this is the analog of sigma qi log qi over pi. So this is the relative entropy of lambda with respect to mu. Of course, this need not be well defined, because for this to be well defined, several things has to happen. I mean, lambda must be absolutely continuous with respect to mu, so that you can write down the Radon derivative d lambda over d mu. Okay, that's well defined. Then you could log d lambda over d mu. That's some function. It's not necessarily non-negative, but that function has to be integrable with respect to lambda. So, if that's the case, this is well defined. If that's not the case, you can define this to be plus infinity, and you can check that's a consistent definition. Okay. So this object is always well defined, although it could be plus infinity. It's never negative. Jensen's inequality tells you it's always non-negative. Okay. So this sort of is the final version for independent random variables of large deviation, because it sort of tells you, if you draw independent observation for any distribution, what is the probability that the sample looks like it came from some other distribution? And that probability is exponentially small, and this is the exponential rate. Okay, then a slight shift takes place, and then the next idea for large deviations comes in a slightly different context. In a paper published in 1964, Strawson proves the law of the iterator logarithm for the invariance principle. So it's, classically there's the central limit theorem, and then there's the Donskoy's invariance principle, which is a functional form of the central limit theorem. So Strawson is looking for a functional form of the law of the iterator logarithm. Now, for those who know the intricacies of the law of the iterator logarithm, it says something or other is equal to square root of 2. And one of the mysteries is, where does the square root of 2 come from? Well, the square root of 2 comes from because the Gaussian density is e to the minus x squared by 2, and x squared by 2 is 1 when x is square root of 2. That's not very revealing, but that's what the proof depends on. So what it is really large deviations. In large deviations, the probabilities decay like e to the minus a squared by 2. So the probability is roughly e to the minus a squared by 2 times n. Turns out n is really log n. So if you work it out, it looks like 1 over n to the a squared by 2. And then you want to apply Borel-Cantelli lemma, this series summation of 1 over a squared by 2 should converge, and the critical value is when a squared by 2 equals 1. So that's how a equals square root of 2 comes up in the law of the iterator logarithm. So if you want to look at the functional form of the law of the iterator logarithm, you have to look at how probabilities decay. What is the exponential constant at which rate the probabilities decay? And that's precisely a large deviation question, as we saw. So Strawson had to look at Brownian motion with a small variance and examine how the probabilities decay for it. That paper appeared in 1964. But there is also the work of Schilder, which was quite independent of Strawson's work, but appeared around the same time. Although Schilder's work appeared in 1966, this was done in 1964. He was a student of Donsker, and he was interested in the following problem. You look at the behavior of a function of this type. So you look at Brownian motion, you look at multiplied by square root of epsilon. So that means this is a Brownian motion with a very small variance. And then you look at some function evaluated at that point. You look at 1 over epsilon times that. So this is a very big function. And then you take the expected value of that, which is very big. Take the log of that, which is still big. Multiply by epsilon. Maybe now it's not so big. And then you look at the behavior of this as epsilon goes to 0. Now this comes up in analyzing some asymptotic behavior of solutions of certain PDEs and so on. I don't want to get into this at this point, but this is really asymptotic behavior of certain function space integral. So if this were finite dimensional, you could write this as epsilon times log of an integral of this object multiplied by the density. Let's pretend that the density is this. It's not unreasonable because Brownian motion is a Gaussian process. Gaussian process has covariances, a Gaussian distribution with covariances have a density, and the density is e to the minus 1/2 x A inverse x, or A is the covariance. So all you need to know is the quadratic form that goes with the inverse of the covariance kernel. The covariance kernel for Brownian motion is min st, and the inverse of min st is the second derivative, and the quadratic form that goes with the second derivative is the square integral of the first derivative. So all this is fairly simple functional analysis. So you can think of the Brownian motion as sum with this integral, except what is involved here is an infinite dimensional Lebesgue measure which doesn't exist, and this quantity is almost surely infinite with respect to this, and there is a constant in front which is either 0 or infinity, I forget. Anyway, all of this is irrelevant because this is only a formal expression. But if you look at this formal expression, as epsilon goes to 0, but as a kind of a Laplace asymptotic formula, it's clear what should matter is only the infimum of the combination of V minus this object. And once you know what the infimum is, or rather what the supremum is, then you can evaluate this limit, and the limit should just be the supremum. Because somehow with the exponential you take 1 over epsilon and the epsilon should cancel, and the contribution to the integral should come only from one point, namely where the supremum is attained. The actual proof that Schilder gave was to approximate this by a finite dimensional integral. And for finite dimensional integral, you can write down the Gaussian integral, show the corresponding thing, prove that's true, and then interchange the two limits, providing a fair amount of justification needed for that. But Strassen essentially had to show that the probability that a small Gaussian is close to a path is given by this formula. And he needed that in order to prove his functional iterator logarithm, and instead of square root of 2, he is going to get as the set of limit points all paths for which this integral 0 to t x prime t squared dt is less than or equal to 2. So which is the analog of that set. And so that's the relation to Schilder's work and Strassen's law of the iterator logarithm. They were done more or less independently. So the finite dimensional approximations are used in order to interchange the limits. So this was about the time when I came to New York as a postdoc and got interested in what was going on in large deviations, Schilder's work in particular, and trying to put it in some kind of a general framework. So if you have a family of functions which you want to integrate, so the function is in the exponential and there is a large factor in front of the function, and you have a large class of measures, and you want to do this integral and study it asymptotically as epsilon goes to 0. Now I would like to understand first of all what is meant by p epsilon behaving like this for some function I of x. Suppose I could find some possible definition of it, then I would expect the integral to behave the way it did in Schilder's theorem. So the question is, what kind of an assumption you should put on the behavior of these probability measures so that you can make this conclusion. Once you formulate it that way, the answer is not that difficult. Just like you have to do the analog of weak convergence in the sense of Prohorov and his Russian school. So what you need is that for closed sets, the probability should behave in a certain manner, with lim sup being less than or equal to what it should be. And for open sets, it should have the behavior in the opposite direction. And if you put the two together, you need some regularity, which is the level sets of this function should be compact, which means the function is coercive in some sense and lower semi-continuous. Once you have all these things, then you can establish that the integrals behave in the right way. So the question now is, if p epsilon is the distribution of the Brownian motion with small variance, then is this true? And so you can interpret Schilder's results, and basically this is what Strawson does too, and the proof is, once you know what to prove, it's not that hard to prove. And if you want to know when the probabilities actually decay exactly, just like the notion of continuity sets in weak convergence, here your notion of continuity set is the infimum of the function I over the interior of the set is the same as the infimum over the closure of the set. Once you have that, then you have a precise exponential decay for this probability of the set, which would have this form. Okay. Now, you realize that Brownian motion is, after all, the fundamental solution for the heat equation. See, Brownian motion plays two roles. At one level it's a Gaussian distribution, at one level it's a diffusion or a Markov process. So far our calculations have been based on viewing Brownian motion as a Gaussian measure. So now I want to think of Brownian motion as a Markov process, as a diffusion process, so it's governed by a generator which is just the heat equation involving the Laplace operator. So I can replace the Laplace operator by a more general second order elliptic operator of this form. So when Aij is delta Ij and Bj's are 0, that's just a Brownian motion. In this case, we know that the fundamental solution, which is just the transition probability, behaves in this manner. Which, if you are willing to forget about all these guys and you only want to concentrate on the exponent, then you can interpret it in this sense. Now the question is, how does it behave in the general case? If you replace Brownian motion by the fundamental solution for such an operator, then can you tell how this thing behaves? Since we are talking about history, there's a little story to say about how this came about. I think it was 1965 sometime when those days Mark Katz used to be at Rockefeller Center, which is across town from NYU, and we had a joint seminar. I think it was every Tuesday afternoon or something like that. We would go up there one week and they would come down another week. It was one of these seminars. I was there and we were coming back in a taxi, and somebody was explaining a result of Cheselsky, which says if you look at the ratio of the fundamental solution of the heat equation, namely this, to the same fundamental solution in a region with Dirichlet boundary conditions, that means the Brownian motion is killed when it reaches the boundary, then that fundamental solution, which is the Dirichlet fundamental solution, by maximum principle is always less than or equal to this. And if you look at the ratio of the two, that's less than or equal to 1. And then the question was, if you look at the ratio and let t go to 0, when does the ratio go to 1? Katz was interested in it. It's known as the principle of not failing the boundary. So the question was, when is that true? And Cheselsky's theorem was, essentially that's true if and only if the region is convex. It's true for all x and y if and only if the region is convex. If you think about it a little bit, if the region is only convex, that means straight lines joining x and y stay inside the region. And if you think a little more, then you realize that if a Brownian motion goes from some point x to another point y in a very short time, which it doesn't want to do, but if you force it to do it, it will go in a straight line. That's, of all the unpleasant alternatives, that's the least unpleasant alternative. Then, if you think about it, if you replace Brownian motion by something like this, you are changing the geometry. And if you change the geometry, then the path, instead of going along straight lines now, should go along the geodesic. So the idea then is the corresponding generalization for this should be that the asymptotic behavior of the fundamental solution now should give you the square of the geodesic distance between x and y, the geodesic computed with respect to the metric that goes with the coefficients aij. The b's don't play any part, they become negligible for small t. So this is basically the large deviation corresponding to, is the diffusion analog of Strauss's result if you want. So what we are doing here is looking at a measure that corresponds to epsilon times L, where L is the differential operator corresponding to the diffusion. Epsilon times L means really you are looking at small time behavior, because we replace L by epsilon, your time slows down considerably. And then you have exactly the same analog that we had for Strasson's theorem or Schilder's theorem, except the rate function now, instead of just a square of x dot, it's x dot calculated in this metric. And then if you are interested in the distribution at time 1, you minimize this with respect to over all paths, which x0 equals x and x1 equals y, and that gives you the square of the geodesic distance. And the minimizing trajectory is the geodesic. Not only the geodesic, it's geodesic correctly parameterized so that you cover the distance at uniform speed. Now, of course, there are various places to put epsilon, and you can put epsilon in front of the second order term and not in front of the first order term. Here what you are doing is a slightly different problem. It's not you are looking at it at small time, or you are looking at small noise. You are looking at small noise of an ODE. So if this term were not there, this would be a first order operator, which would correspond to an ODE or a dynamical system. You are perturbing a dynamical system with a small noise, and you want to know what is the effect of it. And it's clear that what should happen is really, the rate function would change in this manner. There are various ways of seeing it. The simplest way, perhaps, is to make a change of variables and get rid of this. You can make a time-dependent change of variables and get rid of this. But to guess the formula is not that difficult. Now, the history of this is when B is 0. I did the work in 1967, and then Wenzel and Friedlin during 1969 and 70 analyzed this problem completely. I'll come back to their work in a little bit. And in 1970, a student at NYU who worked with me also did this in his thesis. And I believe these were all done more or less. I think Wenzel and Friedlin did their work fairly independently, and it just happened to have around the same time. Okay. So Wenzel and Friedlin got interested in this problem in order to study what's known as the exit problem, which is quite an interesting problem. The idea here is you have an ODE driven by some vector field. and you started at some initial value. And all solutions converge to a stable fixed point in x0 in a region G. So imagine x0 to be sort of the center of attraction of everything that's around it. Then you look at L epsilon, remember, was the first order operator perturbed by epsilon times a second order operator. The second order operator, even if there is an epsilon in front, being elliptic, would have a nice solution to the Dirichlet problem, and so it would have a harmonic measure. You denote the harmonic measure by this. The harmonic measure is for the region G, so it would be concentrated on the boundary of G. You want to know what happens to the harmonic measure as epsilon goes to 0. As epsilon goes to 0, only the vector field remains. The noise disappears. If the vector field took you outside the region, then you follow the vector field, it will get out of the boundary at some point, and if you add a little noise, it will still get out near that point. So you know that the limit of the harmonic measure is going to be the delta function of where the vector field gets out. But I have a stable fixed point inside, and the vector field is flowing inside. So if I let epsilon go to 0, vector field does not get out. So you're forcing something that doesn't want to get out to get out. So you're forcing something to do that it doesn't want to do. So what does it do? One should think that what it will do is the least undesirable thing. Okay? So that's the point we want to emphasize here. So what that means, you look at the rate function and you minimize the rate function starting at the equilibrium point and ending at some point on the boundary. Of course, the rate function for this will never be 0 because the only 0 paths are paths of the ODE which all want to come to x0. Nothing wants to go out from x0. So anything that goes out of x0 will have a positive I. But still you can look at all these things and look at the least favorable, least undesirable among these. Whether of course will depend on how much time you give it. Take the infimum over all time too, and then you would get a function. And this of course depend on which point on the boundary you want to get to. Give it that charge too, and take the infimum over all y, and you get a function. You get y naught where the v attains its minimum. So this is sort of the least undesirable point to get out of, and the result of Wenzel and Friedlin is that's where it gets out. Of course, it's going to take years and years for it to get out because it doesn't want to get out. So the picture one has in mind is really very nice. It sort of describes why large deviation theory is useful, because what it does, the point speeds very fast to the equilibrium point, at least normal speed. It hangs around there for a very long time, making small excursion. Each time it gets out, it gets pushed back. Each time it gets out, it comes back. Makes various excursions, which are unsuccessful attempts. Finally, the unsuccessful attempts occur randomly with these probabilities. So there are various levels of probability, infinitesimals of different orders. All these things are occurring. Some of them are successful, some of them are not successful. And you get out at the first successful thing. And the first successful thing is going to be the one for which the exponent is the smallest. Because the smaller the probability is, the longer you have to wait. The waiting time for an event with this probability to occur is e to the plus I over epsilon. So the first successful attempt will be the one for which I is minimum. So that's why that gives you the point that exits. Of course, you can have several stable equilibrium points instead of just one, then you should think of this as mountainous region with hills and valleys, and the valleys, the bottom of the valleys are the stable equilibrium points, and you have something that's moving around, maybe a marble which rolls down due to gravity, but has some random motion attached to it, so it sort of hobbles around a little bit, so it goes in a random direction, but gravity pulls it down. And then, just due to chance, it gets up to a mountain pass and then drops down to the next valley. So the probability of getting to a height is very small. It's e to the minus the height over epsilon. So the first escape is going to be through the mountain pass, which is the lowest. So that's the optimal way to get out, and just by accident it gets out of the optimal way. So that's the interpretation one has. Okay. So then we go back to another storyline. In 1973, Moni Danske, who I worked with closely for many years, asked me the following question. You have the Feynman-Kautz formula, which looks at the heat equation with a potential, and the solution is expressed as a function space integral. Feynman originally considered with time as imaginary because he came from quantum mechanics side, so there is an I everywhere, and then this function space integral is not really a measure. That's the Feynman integral, but then Kautz said, if you take the I out and make it just delta, then the function space integral is Brownian motion, and then it's mathematically well defined. So that's the Feynman-Kautz formula for the solution of that equation. And then if you want to study the asymptotic behavior of this, you can look at the spectral theorem for the operator O nav Laplace in plus V, analyze it, and see that the growth rate of this function is exponential, and the exponential constant is just the largest eigenvalue, which is given by the Rayleigh-Ritz variational formula as a supremum of the potential energy, and with this energy term as a compensators. So that's the exponential rate of growth. Now Danske's question was, okay, here is a function space integral, and here is a variational formula. Now, is there a large deviation that connects the two? Because we know that whenever we have a large deviation with the rate function, analyze integrals, then you have variational formula coming out. Here we already have a variational formula. Can you interpret it in a large deviation context? Well, it turns out you can, and all you have to do for that is to re-express this variational formula not in terms of L2, but in terms of L1. If you take an L2 function and you square it, it's an L1 function. So you express the variational formula not in terms of G, but in terms of G square. So let's call G square F, and then this variational formula becomes this variational formula. This is just the Dirichlet form with G equals square root of F. Then what you do is, just as you look at the empirical distribution in the Sanau case, now you look at the proportion of time the trajectory of a Markov process spends in the set A in the time interval 0 to t. So this is the empirical distribution, or the local time, or whatever, of the process during the time interval 0 to t. And what you have is really a large deviation for this. The ergodic theorem, pretend that you are in the periodic case, so that, there is an invariant measure and there is an ergodic theorem, so the system is not dissipative. Then the invariant measure would just be the Lebesgue measure. and that would be when I is 0, then f would be a constant, and normalization makes it f equals 1, which is just the Lebesgue measure. And so this is then the probability that the ergodic theorem fails and the averages converge to f or close to f rather than 1. So this is the large deviation rate, and then you can reinterpret the Feynman-Kautz formula as evaluating the expectation of the kind we have always looked at, and then you would get the variational formula. So this is for the Brownian motion, and then during the years 73 to 77 we extended it to a large class of Markov processes, and quite, I believe quite independently, Jürgen Gartner looked at it purely as a generating function technique, and that appeared in 1977. So the formula for general Markov processes, you can also look at it for discrete time, not necessarily continuous time Markov processes. Then the rate function can be expressed in this manner. And in the reversible case, in continuous time, you have the Dirichlet form, which we went through before. And then there's a fairly interesting question that came up, had to do, Mark Kautz was always humorous about coining names, so he called this a Wiener sausage. And here the issue really is, you have Brownian motion on a torus, and we know there is a large deviation with this rate function, but the rate function is in the weak topology, because basically a Brownian motion is a two-dimensional path, roughly speaking. So if your dimension is 2 or more, these local times don't have densities, they are singular measures. In two-dimensionality they are singular. But you can convolute it with a small distribution phi t and smoothen it out, then you have a density. So now, how much are you allowed to smooth it? Turns out, in d dimensions, for the problem that he was interested in, which is a problem that came from trying to analyze the density of states in a problem of random Schrodinger operators. The technical issue that came up was that if you convolute it with a small modifier which went to delta function at this precise rate, then can you improve the topology from weak topology to L1 topology? So there is an interplay between this kind of functional analysis questions and large deviation questions, and they can be handled as well. Now, one of the important ideas in large deviations is so-called contraction principle. It's not very difficult to understand. If you have a large deviation upstairs in a space X, and you have some kind of a continuous map from X to Y, you can figure out what the large deviation rate should be in Y. Because if you have a function on Y, you can lift it to a function of X. Any integral you want to do, you can do that. And you know what to do here, so in principle you know what to do here. So it's just a question of sitting down and doing the calculation. And if you do the calculation, you see that the rate function here is just, you look at the inverse image there and look what is most advantageous to you. The infimum of the rate function here on the fiber gives you the rate function downstairs, and that's not hard to see. Then we go to what is called Shannon-Bremen-Mcmillan theorem in information theory, which has been around for a long time. And what it is is the following kind of calculation. You have a finite alphabet, which is just a bunch of sets. Think of it as 0 and 1 if you want to. Then you look at words of length n, which is just strings of alphabets of length n. And then f infinity is the doubly infinite sequences rather than just finite words. Then you start with an ergodic stationary measure on this product space. That means shift invariant and ergodic. And mu n is its restriction to blocks of length n. And then you can calculate the log of the mu n of w. You think of it as a random variable because w can still vary over all possible sequences of length n. You can view it as a random variable and you normalize it by 1 over n, and this random variable converges in probability to a constant, and the constant is just minus h, where h is the Kolmogorov-Sinai entropy. That's the Shannon, Bremen, Mcmillan theorem. And one should really think of this as the ultimate large deviation result. Try to explain why. The ergodic theorem says words of length n will have substrings of length k. Most of them would have the proportions would be close to mu k. That's just the ergodic theorem, not just for length 1, but length 2, length 3, any length whatsoever. So long as you fix k and let n go to infinity, you can use the ergodic theorem. What it says then is, since most of the words of length n have probability roughly e to the minus nh by Shannon, Bremen, Mcmillan theorem, this is the number of such words. So this is just counting. You're counting words of length. How many different types of words are there of certain type? So if you think of lambda as a product measure, uniform distribution on F, then the probability under lambda that a sequence of length n, which should with very high probability look like lambda by the ergodic theorem, what is the probability it looks like mu instead? You just count, just combinatorial counting, and the number is given by the Shannon, Bremen, Mcmillan theorem. And if you count it and calculate the rate function, it's just this. You can reinterpret this because there is another way of calculating the rate function. Kolmogorov-Sinai entropy can be calculated as the average conditional entropy. So you calculate it in that manner. Is another formula for h of mu. And you can rewrite this in this form. I write it as lambda alpha omega, but lambda is a product measure and uniform. So lambda alpha omega is just 1 over k, no matter alpha and omega are. They're independent. The conditional distribution is the unconditional distribution. It's uniform, so it's just 1 over the number of elements in the alphabet. But on the other hand, if you write it in this form, you see immediately how to generalize it. If you replace lambda now by an arbitrary stationary process, it doesn't take much thought to see how to generalize this, because it's already generalized. Okay. And for a Markov process, then you know exactly what lambda alpha omega is. It just depends upon the last element of omega, and it's given by the transition probability, and you can rewrite this in this manner. So this is what the large deviation rate function is for If we generate a Markov sequence, what is the probability that the empirical process looks like mu? Once you have it, then you can contract from it and just get all the earlier results about just the one-dimensional distribution of mu or the two-dimensional distributions of mu and anything you like. So notice that the advantage here in this formulation, this rate function is almost universal. It doesn't, it expresses by the same formula all lambdas. It could be product measure, then it would be Sanov, it could be Markov, or any kind of dependence whatsoever. I think I should speed up at this point. I think I should. Okay, I think I should get to my conclusion. So in an extremely complex situation, the idea is you have a model. The model has a typical behavior, but you are interested in the probability of a large deviation, which is a behavior just not typical. So what you should do, whether it is Escher tilt or whatever you do, what you need to do is change the model. Change the model so that the behavior, which was a large deviation behavior, now is in fact a typical behavior. And then you measure the distance between the models in some sense, by Kullback-Leibler relative entropy kind of a distance, and that should roughly tell you what the large deviation rate function is. But of course, there are a lot of ways of changing the model, and you should choose the cheapest model, the one for which the distance is minimal. So be as stingy as you can, and that would be in fact, what happens is each change of model will give you a lower bound, and you try to be the best possible lower bound you can get, hopefully, is also an upper bound. It's easier said than done, because changing the model, if the problem is very complex, you can't really afford to do all change of models. You have to be a little bit clever and see what are the most relevant change of models. And that takes some experience and some effort. I guess we are at the end. Thank you.